Here is Peter Bartello from McGill with his title Between Quasi-Geostrophic and Stratified Turbulence. Thank you.
Thank you. I guess the microphone is on. It sort of sounds like it. Anyway, thanks to the organizers for having me. It's always a pleasure to come here. I want to talk about turbulence, and really mostly this stuff is about numerical simulations. Will this work? Yeah? Okay. The great thing about this room is it has a very big stick, and we often like to measure the slopes of spectra in my biz, and it's very, very useful for that. Here's some old data from the atmosphere, and probably all seen this before, but the whole story is that quasi-geostrophic turbulence is pretty well understood, and what it looks like. It gives a steep energy spectrum. But the surprise in this old data was this shallow range in the mesoscale, okay? And it starts at 300 kilometers in horizontal scale. And it's far from, it's a minus 5/3 range, and it's far from isotropic scales. And here's some newer data of the ocean. Unfortunately, it's not the same thing as shear, okay? So it's, the spectrum is k squared times the energy. And so minus 5/3 times k squared gives you plus 1/3. And you can see there's some steeper range at larger scales and something approaching minus 5/3. Once again, at scales that are not are too large to be isotropic. So I want to talk about playing around with that and trying to figure it out, and well, something consistent with it at the very minimum. I'm just going to talk about triply periodic Boussinesque. I mean, triply periodic in the density fluctuations, not the basic state density. There's geostrophic and hydrostatic balance, and here they are. The notation I'm using, there's two things: the Rossby number for rotation and the Froude number for stratification. My title says I want to go from quasi-geostrophic turbulence, which means strong rotation and strong stratification, to stratified turbulence, which is where we turn the rotation off. And the reason I have such a title is that's the folklore in GFD. Is that because n over f is 100 in the atmosphere and 50 in the ocean, as you go down scale, you lose the importance, the predominance of rotation before stratification. So I'm going to think of this as this regime between these two limits. Here's the limits. Now that I've talked about Charney, QG is like 2D turbulence with all that stuff we know and love. And it's also true that in this low Rossby, low Froude range, these wave modes, this fast energy, high frequency inertial gravity modes cascade downscale. What you may not know is there's been a bit of movement lately in the last 5 or 6 years about the limit where there's no rotation, it's just stratified turbulence, okay? And I want to talk about that for maybe a little longer. The classical stuff that you might have read, if you're old enough, if you're as old as me, is just based on taking this Froude number, which I'm now going to call the vertical Froude number because I'm going to introduce another one. The Froude number is usually defined in terms of the vertical shear, right? du dz, d horizontal velocity, d vertical direction, and n is the Brunt-Vassallo frequency. And Lilly did these asymptotics. He created this wave. I mean, he used this this time scale for the wave, and it's of course 1 over n, but it's modulated by h over l. I forgot to mention the dispersion relations here for the Boussinesque set. So there's it's n if the wave vector is horizontal and f if it's vertical. So if I have a typical horizontal scale and a typical vertical scale, then I get this frequency, which is essentially this. And we use the advective time scale. And if you look at the two, you get the ratio is just this vertical Froude number. And so what Lilly did was derive this limit, and he gets, I'll show you the equations in a second. And McWilliams came out a couple of years later and said this whole idea of geostrophic balance can work nicely, nice and cleanly. There's a nice smooth evolution to stratified turbulence. And that's because of this timescale disparity, right? We're doing asymptotics for that thing small. More recently, people have introduced another Froude number, okay, and I'm going to call it the horizontal Froude number. It's identical, except it's horizontal scale and not a vertical scale. And two limits that have been under discussion is this is the Lilly thing I was talking about, and we have this timescale disparity and some consequences on the various terms and the potential vorticity, which I don't really need to go into too much. More recently, our attention has been fixed on this idea, which is the vertical Froude number stays 1. Okay? As n goes to infinity, the stratification gets bigger and bigger. The vertical scale gets smaller and smaller, such that their product is fixed. The vertical Froude number is fixed, so you can't use it as a measure of stratification. So we use this horizontal one instead, because people seem to have been seeing that the horizontal scales are much less affected. So that gives us a vertical scale. The vertical Froude number is 1. And there's a bit of history there. So here's what it looks like. Okay, this limit number 1, which is the Lilly thing, is that all the colors go away. Okay, and what's going on is I've just written anything that looks like a vector is just the horizontal part. I've written the vertical part out explicitly. So that's just these are the equations that usually are referred to as layer-wise two-dimensional. So it's just horizontal advection. Horizontal divergence is 0. So classic thing in GFD. The new and improved limit is that we keep all the vertical advection terms. We just throw away the horizontal Froude number. That's going to 0. Vertical Froude number stays order 1. Vertical advection never goes away. Horizontal divergence is not 0. The conserved quantities in these two limits are very different. And so for a turbulence person, cascades we expect are kind of different. You still have hydrostatic balance in that limit. Now the point I want to make and I want to stress is that if we're non-dimensionalizing x and y with some L and z with some h, and h is much smaller than L. So the dissipation term looks like this, which has got the usual Reynolds number in front of the horizontal, x derivatives and y derivatives. But it's got this new monster in front of the vertical derivatives. And that's what this is. It's the regular Reynolds number times h over L squared. Now, if h over L is going to 0, you could have pretty small, this is, by the way, we call it the buoyancy Reynolds number. So it's possible that it's more demanding, okay? H over L is going to 0, but the Reynolds number is kind of biggish. But if h over L is small enough, then the term kicks in. If the term kicks in, then we're not talking about atmospheric and oceanic dynamics, where the Reynolds number is quasi-infinite. We're talking about sort of viscous behavior, okay? So the question is, which limit is right? I want to talk about some very old results, but we measured this in a simulation a long time ago. And we also saw in another paper that this Osmodov scale, which is the smallest scale that's influenced by stratification, below the Osmodov scale, you have isotropic turbulence. And it's just basically epsilon over n cubed, the square root of all of that. And we measured its dependence on the stratification. And you can deduce from that graph that epsilon, the energy dissipation, is independent of the stratification. Okay? And then there's another paper by Eric Lindborg that came out that said, rather speculatively, in my opinion, just said that the whole horizontal statistics are unaltered Kolmogorov statistics. Okay, that the stratification just changes the vertical. But in the horizontal, we expect to see epsilon to the 2/3 kh, the horizontal part of the wave vector, to the minus 5/3. And that's sort of consistent with his point number 2. But I thought I'd try playing around with this. And Steve Tobias came up to me last time I gave a seminar in this room and said, hey, let's do it. So we did some very high resolution simulations. And so here's the two issues. One is the horizontal Froude number, which measures the stratification. And the other is this Reynolds buoyancy number, which is the prefactor on this vertical dissipation term. And we always wanted to keep this above 1 so that we're in a high Reynolds number limit. But even with an enormous grid, this is 2048 squared by 513 using 768 processors, something that Steve knows how to do, but I wouldn't touch with a barge pole. But it's still very hard to get buoyancy Reynolds numbers that are very, very big. And the point we want to make is we just looked at the energy spectra from a bunch of simulations, and we get what everybody else has gotten in the literature in the last 10 to 15 years, is that the spectrum is steeper when the stratification is stronger. However, that's very misleading. So we decided to do another set of simulations. This is one stratification, and that's a stronger stratification. And what we did was we tried different grids and different Reynolds numbers, okay? And so different values of this thing, the buoyancy Reynolds number. And of course, the different Reynolds numbers have different dissipation ranges. And you can see some degree of convergence. This is just scaling it with Kolmogorov. And of course, no cigar, we're not really in any kind of asymptotic regime. Even with these resources, we have somewhat insufficient resolution. So we decided to see how the horizontal spectrum responds to the stratification and the dissipation by just simply measuring the slopes in the range of the spectrum where we sort of expect an inertial range to be. That's just one simulation. There's lots of them. But here's the smoking gun. This is also the lower stratification here and the higher stratification there. And here we're plotting these slopes, and this is medium, low, medium, and higher refer to the Reynolds numbers of these simulations. And here are these slopes as a function of the stratification, so that you can see that at a given stratification, you get different slopes, which is what I just showed you. Same, I mean, they're both more or less the same, so don't worry about it. But this is this buoyancy Reynolds number, which is the...
How do you change the horizontal food number? What's the parameter?
N. And U and L just don't move much. But I mean...
Yeah, I don't understand. You show us two different N's and as a function of FH.
Yeah, well, okay, sorry. Time is what's going on. Yeah. These are decaying, decaying simulations. So here's time series of the Froude numbers. So they're going up and down, and the buoyancy Reynolds number. Okay, I mean, the Reynolds number is determined in terms of all this stuff, right?
Okay.
And they're moving around. Epsilon looks like entropy, that kind of stuff. So it's time that's making them change. Actually, the evolution, if you're interested, the early times are here and later times are there. They're all starting from the same initial conditions, so they're all from the same point. So anyway, the point is the stratification, any different Reynolds numbers give you different slopes at the same stratification, but they all line up nicely when you do it the other way around. All the slopes are responding to is this vertical dissipation term, okay? And this is where these simulations are a little unusual in that we actually got a pointer to in a reasonably flat regime, and everything in numerical simulations, 99% of everything that's been published is down here where this vertical dissipation term is kind of important. And I almost guarantee you that every laboratory experiment in stratified turbulence is way down here, where you get abnormally steep spectra. So it suggests very strongly that if the Reynolds number is big enough, the horizontal spectrum is independent of the stratification. And so I'm going to use that. Okay, so that's, I think, what that says. I'm going to use that as sort of the other end of the limit. Now, we have quasigeostrophic turbulence and stratified turbulence. But stratified turbulence, I'm now going to say, has got vertical Froude number stays 1, no time scale disparity between waves and vortices, none, okay? So no possibility of anything like balance. Okay, so now that we got that, I could report clearly that this isn't what we should be doing, right? Because So this is this idea that Lindborg had, which is that it's just a K41 spectrum in the horizontal wave number. And the vertical stuff is all very much determined by the stratification, but not the horizontal stuff. So I'm actually stealing Osmedov's logic. Osmedov said, if you go down in a small K41 range and you go up towards larger scales, the turbulence gets slower and slower. So at sufficiently small scales, it's much, the turbulence is much more rapid than n, okay? And you can drop n as a dimensional parameter, and you get return to isotropy in small scales. But if we use this Lindborg spectrum, which is the same spectrum, except with an h, and we go up this range, the omega NL is just sort of nonlinear frequency, very classic Kolmogorov relationship there, so that the turbulence is still getting slower and slower. And the point is, this whole thing was devised for no rotation. So we dropped f as a dimensional parameter. So obviously, ultimately, you hit f, okay? And then after that, this is obviously no good. We have to consider rotation. Well, we can use some estimates of atmospheric. So this is just the same relationship switched around in terms of not a wave number, but a scale. And we use some recent, some observational stuff. In fact, you can just read it off of that first graph I showed you. And f, mid-latitude f. And we get that this scale where you've got to start thinking about rotation is only order 10 kilometers in the atmosphere, okay? And the Nystrom gauge, the data has a shallow range starting in a few hundred kilometers, okay? So it's not this, all right? So I think we're here when we talk about the large end of that shallow range. And so this was maybe a bit of a barking up the wrong tree. Well, a long time ago, a former student of mine, Mike Waite, and I did playing around with some of these vertical length scales. And we measured the vertical length scale in a bunch of simulations of kind of 10-year-ago resolution, okay? So it's not super high Reynolds numbers. But we just compared them. Well, this is the vertical length scale you get with Froude number 1. These are the Rossby numbers, okay? That's the whole idea here, is we're turning the rotation up and down, but we're keeping very strong stratification. Okay, and so what happens is the vertical Froude number is 1 is sort of the large Rossby number limit, which is what the simulation does. And then this is just Charney's expression for the deformation radius, only switched around so as to solve for the vertical scale. And so that gives us this curve, and you can see that the simulation jumps from the stratified regime to the quasi-geostrophic regime. And of course, this point where they meet is Rossby number equals 1, right? Has to be. So anyway, that can happen. But really, more interesting to me was, can we actually use a computer in the modern era to very cleanly simulate a flow that is quasi-geostrophic in the large scales, but that breaks down to something else more general in the small scales. And then, if so, what does it look like? So I'm going to skip all of these legalistic things about the simulation and just try to tell you about them as I go along. This is a simulation where we took n over f is equal to 10. It's supposed to be 100, but I can't afford it, so I knock it down to make it cheaper. It's done in a periodic box whose aspect ratio is the same, 10 to 1. It's n over f is 10. And we're forcing a baroclinic mode, geostrophic baroclinic mode, which also has that same aspect ratio. So all the large-scale stuff is all following classic QG. Is that a question?
Yes. How beautiful is the resolution? Because this curve is like idealistic, you know.
This scale?
The curves are so beautiful. I mean, so clean, so curved.
It's well, I mean, the resolution is a couple of decades, right? it was something. It was not super high, but I use hyperviscosity. Okay, that's a cheat we do in GFD that the turbulence community really hates. But
And these curves done average over time?
oh yeah, no, they are. It's all statistically stationary and average.
I don't see any fluctuations in any place. It looks like.
Well, I'll show. Hold on. Here, look.
No, just.
See, that's what they look like, okay? So that one there on the left, I'll show you in a sec. But anyway, I haven't talked about this one yet. These are the difference, but those two pictures was one up here and one down there, okay? And it looks like turbulence, believe me.
I think he's saying the curves are really smooth.
Yeah, but they're averaged over time, and that's just the way it is. This is a quasigeostrophic limit, okay? That's a very, very high rotation of stratification. The ratio of the two is always 10, but I'm turning them both up and down proportionally. And as I turn the N and F down, the tail of the spectrum flies up, okay? And here's the top curve here is repeated there. And I could just simply decompose this flow into high-frequency wave modes and geostrophic modes, okay? And the geostrophic modes have this green spectrum, which comes down here very steeply, and by the way, this is log-log plot, so all the energy is in these 2 points, okay? And this flow is quite quasi-geostrophic. But the geostrophic modes have a very steep spectrum and a potential entropy cascade a la Charney. It all looks great. At the same time, these fast modes have this spectrum, which is like that, and it's very, very close to minus 5/3, okay? And what happens is the geostrophic modes cross over, and eventually, now I'm kind of appealing to theoretical arguments, but since the linear decomposition has no meaning at really high wave number because the flow is so nonlinear, all you should see is they're following the same curve, they're parallel, and there's a ratio of 2 to 1 because there's twice as many wave modes as there are geostrophic modes. So we're seeing something like that. And this is the picture without any boundaries, okay? But it sort of seems consistent with the observations. Okay, so there's a picture of the QG flow looking down on the vertical vorticity, looking from the side. There's my aspect ratio. And then this is the one that's the one with the larger Rossby number, right? So this is this guy here. And it looks a lot like John Methven's bands and stuff. I mean, that kind of, you look at QG flows, and John showed an SG flow, nice and smooth, beautiful, nice filaments and stuff like that. And you look at these kind of flows, or the Met Office model, and you see stuff that looks like this, okay? So it's not unusual, and it's not super new.
Rossby number of 2 would be rare in the metaphys.
Yeah.
Well,
yeah,
I 1.5 kilometer grid. I'm giving them some quite large Rossby numbers now.
I regret that I used RMS vertical vorticity to define my Rossby number. And I think I'm going to stop because the numbers I'm getting are like 10 times bigger than if you use U and L, right? I always find this rather annoying about length scales in turbulence simulations. You tell me what one you want, and I'll define the length scale that gives it to you. All right, so I got a little bit of hassle last time I was in the UK from balance fanatics because I forced the geostrophic modes, okay? There's my forcing, those are the geostrophic modes. And I didn't force these guys, and if you can imagine, that is not a balanced forcing, right? If you imagine just putting the n to a constant and solving those trivial ODEs, you see you get e to the I omega t kind of solutions all over the place. And that this is, randomly pumping up a baroclinic geostrophic mode is not exactly how the atmosphere is forced, okay? So I've since then thought a bit about trying to look at this kind of stuff from a more balanced kind of initial condition. Okay, those were indeed forced simulations, and now I'm going to switch and talk about decay simulations because I can't really figure out balanced forcing for the moment. So I'm going to look at decaying turbulence in very similar kind of context. Let me just define, I got to define what I'm doing. Geostrophic modes on an F plane, okay, there's no Rossby waves. And then this is the gravity inertial dispersion relation here for the ageostrophic mode. Classic stuff. Introduce a slow time scale. We get that. A's have to be order Rossby number. Epsilon is Rossby number here. Then we write it all out. We have all these terms, and they're all various orders. And then you have the slow manifold. You say the ageostrophic modes in balanced flow are given by the geostrophic modes and the Rossby number. So you rewrite this term like that. And this is just the right-hand side of that, right? And you stick that up there, and that's the superbalance equation. And it's you could show that there's an epsilon in front of the biggest derivative, so it's singular perturbation problem. It caused many people to question the existence of the slow manifold, and I don't want to go into this stuff. It was big 20 or 30 years ago. A lot of people studied it with low-order dynamical systems, but I want to come back to it from a turbulence perspective. But I think the prevailing thought about this is that maybe it doesn't exist, but it's a kind of approximately useful concept. We don't see flows that are too far away from balance. So what I did, and I guess I should go back. What I did was look at some very old literature in numerical weather prediction about how to create balanced initial conditions. So we started off with a quasigeostrophic simulation. And that's giving us the G modes, right? Just the G modes. And then we decided we wanted to put that into a non-hydrostatic Boussinesque simulation. So if you want to do that in a balanced way, you have to put in the A modes, the ageostrophic modes. But the ones that are balanced, the ones that are given by this. So we have to solve this equation, and that's a rather tall order, but there's this couple of things going on in the NWP world. Initialization. There's a scheme due to Mackenhauer 77, which essentially just throws that term away. Says, well, we want this to vary on the slow time scale, so let's throw that term away, which is not a very good approximation. However, it has the asymptotics. If epsilon goes to 0, it has this balance here, and so it retains that. There's another one due to Baer and Trivia, which is this to order epsilon squared. And I just want to show you, I'm in the midst of, I did all this with this bad Mackenhauer scheme, and I'm in the midst of converting it and looking at this other one. And any other balance, everybody has their favorite recipe for balance, of course, and I think I could get old coding them all up. But I just want to show you some very short simulations. There's Mackenhauer on the right and Baer Trivia on the left. Baer Trivia on the right. The Rossby number here is 0.66 based on the vorticity again, which makes it artificially large. Oh, I just realized I got the wrong graph here. It says 0.99. It's supposed to be 0.66. This comes, oh, sorry. Oh, let me just drop that then. I was going to show you two different Rossby numbers, but I can't. Anyway, what I find, so that's just the same one as this, isn't it? Yep, they're identical. Okay, so let's just compare them at 0.99. What's going on is this is a geostrophic modes, and this is a very short simulation, non-hydrostatic Boussinesque, okay, for about less than 1080 turnover times. This is the balanced initial condition is the one that looks like this. It comes down there. It's on the bottom. Okay, and this with the Baer Trivia balance, it's more or less the same picture, right? And what happens is the evolution is immediately away, especially in the tail, where it wants to be much, much more shallow. And this is actually quite a long time for this part, and it stays more or less where the initial balancing act put it, right? It stays in there. But the tail seems to want to jump up. And I wanted to show a bit more about that.
Can you explain the colors, please?
Okay, blue is the geostrophic mode spectrum, okay? That's a classic result, very consistent with all the literature on that. And I think there's some kind of sky blue thing here, which I can barely see. which goes like that, and that's a t equals 0 ageostrophic modes that came from this balancing procedure. And then the red ones are subsequent times, and what they do, and I don't think you can see it very clearly, but they go from the low to the high. Okay, so the evolution is to have a tail that's much more shallow. And I want to show that to you again and again and again with different varying in time and stuff like that. First of all, do you believe this is anything like balance? And here's one of these Mackenhauer ones. What's going on is this is just the ageostrophic modes, modal energy. Okay, so I don't throw the geostrophic modes away from the picture. There's the t equals 0 curve, this funny, weird green color. And what's done here, and these are simulation evolution of that. Now, the ageostrophic modal spectrum goes down significantly. We know why. That's because in the inverse energy cascade, the geostrophic energy is roughly conserved, but the scale, the integral scale, is getting larger and larger. So the Rossby number is going down. The scaling is, the ageostrophic amplitudes are proportional to the Rossby number. So as the Rossby number goes down, the ageostrophic spectrum has to drop like a rock. And so that's what happens with the red guys. Now, if the next thing we did was to scramble this initial condition, scramble the phases, which means the spectrum is exactly the same, but it's no longer balanced, not even close. This balance is very sensitive to the phases. So it's just a random field with the same spectrum, okay? And that's the blue guys. And the blue guys come down here, but once again, the tail goes flying up. Now, you might also notice that as these red guys are decaying, late in the simulation, this sort of more shallow, a hint of a more shallow range is appearing. But it's But if I change the initial conditions from balance to just random ageostrophic modes, there's a huge difference, right? This is a log-log plot. You know, that's something like 3 orders of magnitude higher and much, much more shallow, okay? You can see that not only by the tail flipping up, but by the peak coming down. So it is, in fact, quite different whether I do this thing or not.
The shallow bit in the red curve at the end, I mean, is that just the paucity of your balance relation?
My claim is going to be that whatever you do, it's going to come out. You might have to wait longer, or you might have to have larger Reynolds number, but you'll see it.
On the balance scale is not valid down in that.
It's not valid.
Scale analysis justified balance is completely invalid down in that tail, presumably, so you wouldn't expect it to be balanced.
Well, that's not what you hear from David Dritchell.
Yeah, but
Yeah, sure. No, I mean, I'm with you. Here's another one using bare trivia. And all I wanted to show you at this stage is that I'm increasing the Reynolds number. Okay, so here's this evolution from the red guy is the low Reynolds number, and his initial balance spectrum is up here, and all it does is monotonically go down. And there's maybe a hint of a more shallow range occurring there, but I frankly can't see it from here. But the point is, so we don't see any shallow range in that case. The Rossby number is low enough, blah, blah, blah. But all I have to do is move the dissipation wave number out by increasing the Reynolds number. It costs more money. You've got to have a bigger grid. And then I get the blue curve. And the blue curve is going here. That's t equals 0. So right away, bang, up high. In the large scales, the evolution is quite parallel to the red curves. They are a little bit to the right and a little bit higher. This is simply because the geostrophic flow that we used to initialize this model has lost less energy at high Reynolds number than it did at low Reynolds number. Okay, that's something to be expected from QG turbulence theory. But the point is, the shallow tail emerges at larger wave numbers, and if you have infinite Reynolds number, I'm pretty sure you'll find a shallow tail somewhere. So it would be nice to know how that changes as a function of Rossby number. I'm getting close to the end here, but I want to show you 20 in turnover times, okay? So I don't know how to tell you what that is in dimensional terms, because there's only one of these simulations where that corresponds. I think of these things at different Rossby numbers as being basically a minimum and maximum scale, which I'm moving up and down, you know, from 2 kilometers to 2,000 kilometers or something like that. But these are a bunch of simulations where the geostrophic modes all look the same. So I have a bunch of Rossby numbers where the geostrophic modes at the level of this log-log plot are not doing anything particularly different. Okay, and what I've plotted here is the ageostrophic modes divided by the Rossby number squared, which is the scaling that we expect at after 20 turnover times, which is quite a long time from turbulence perspective. The turbulence is very developed. And you see that at low Rossby numbers, the order here is the same as the order here, right? So at low Rossby numbers, they stay very, very steep. And as I increase the Rossby number, bang, this tail pops out. And you could argue that I'm not too sure about this. The resolution is insufficient. And we're doing this now at 4 times the resolution. But I'm hoping to be able to nail the transition as a function of Rossby number. But it
Can you express that as a sort of convergence rate to balance as Rossby number tends to 0? Certainly it could be written like that.
yeah, right.
Then the question is it the expected convergence rate? I
Yes,
know how
yes. That's like one of our first priorities. So I want to, just the last thing, I've got no time left, but I just want to take one of these ones with a kink in the spectrum at high wave numbers and reanalyze that. Of course, I've got the ageostrophic modes, the geostrophic modes from the simulation. So I could take the ageostrophic modes, and I could take the geostrophic modes and balance them again, and subtract the 2, and I get unbalanced, right? And I just want to show you that. So the last time you have to look at this kink in the spectrum. So it's just unbalanced is the total from the simulation plus a new nonlinear normal mode initialization. This is the Macinhauer scheme. And what's going on is the simulation, you can't even see it. It's underneath the balance here, right? And then the simulation, you could just barely see it there for an inch. And then it follows the unbalance here. So the unbalance is some lower thing with a more shallow spectrum. And the balanced ageostrophic modes, see this is what it sticks for, are much steeper, okay? So it's constantly, this idea of balance is always going, and it doesn't matter if you use this Macinhauer scheme to order Rossby or Viertribia to order Rossby squared. It's constantly giving you steep spectra. And you put it in Boussinesq, and Boussinesq says, I don't like that, and it gives you a more shallow spectrum. And so this is, I think, where I'm going to end. And let's see what this stuff says. Okay, first of all, this idea that it's all just the shallow mesoscale range is just stratified turbulence is nonsense, okay? Needs rotation. This is it. If it's balanced, it's steep. That means the geostrophic modes are kind of always steep, okay? So if the ageostrophic modes are steep too, everything's steep. And then this is an old story, this fuzzy notion. It's kind of an approximate, it's not a manifold, the slow manifold. It's something that it doesn't get, the real system doesn't get too far away from. My point is, this stuff is shallow spectrum. I think these two really should have been merged, but it gives you a shallow spectrum and a downscale cascade. I can look at the flux of energy, and it is towards small scales. So it in fact is it's a drain on the large scale balance flow. And the whole idea of this fuzzy notion is, I guess my contribution is to say the fuzz cascades, right? And I guess from a turbulence perspective, that's not too surprising. And all I want to say is that transition to a more shallow spectrum is totally consistent with the data, but at the same time, there's enough people here with enough realistic modeling experience to realize there's millions of things that are missing in what I've discussed. So, but I think it's a worthwhile exercise to solve this problem first, and I'll end there.
Well, we have a few minutes for questions, so please. Yeah.
I guess the argument was that there will always be a kink, but at the scale of the kink, the kink goes to smaller and smaller scales, the Rossby number is reduced. I mean, do you have a scaling for this, the position of the kink?
No. I mean, it's numerical empiricism at this stage. But I'm pretty convinced that that's what happens. But the next question is to actually get the transition scale as a function of Rossby number, right?
And do you have an argument, I mean, do you have a kind of physical argument for why?
Well,
There's also good arguments why things should stick.
well, I know what you're going to. You're probably going to say that the local time scale of k is, as long as the spectrum is steep, it's constant, right? The classic turbulence estimate for the nonlinear frequency is square root of k cubed d of k. However, if you look at the distribution of you can look at the distribution of the time scales, right? And it gets wider and wider as you go down that range, okay? So somehow it gets into a significant part of the distribution is getting into trouble as far as the scaling is concerned. So that's my only lead so far, and that's what I intend to look at.
Right.
Just want to recall stuff that was being talked about meeting in Boulder a few years ago. You referred to some of the people. And so the sort of message I got from that is if you take a scale smaller than the deformation radius and stratification is more important than rotation, then the natural balance limit was effectively 2D or the independent decoupled at each value of Z, and that was a very unsustainable limit because it relied on a large vertical scale, and therefore you have differential horizontal convection wipe it out, and therefore you couldn't sustain that, and therefore you balance broke down. So is what you're saying consistent with that, or are you saying something different?
No, it's totally consistent with that. In fact, that point was made by Mihalov and Nikolenko 15 years ago.
No, that's been around for a year.
Yeah. I mean, this Lilly limit contains within it the seeds of its own destruction, right? I mean,
Well, the Lilly limit does, but not QG, right?
no,
So there's no reason for this to happen.
that's right.
No, but
Well, that's why I got bored with stratified turbulence, right? I want to see how do we get there from QG. Yeah.
So the other quick comment would be that, so on a scale larger, but all the spectra you show were relatively flat at the very large low wave number end, and then they sort of turned over and then started steepening at different rates. So is that now looking at scales larger than the deformation radius, where you wouldn't expect any cascade, so you have a flatter spectrum?
Well, that's not how I think of it. I mean,
You set your problem up, so I'm not sure if that regime even exists.
I never force at the box scale because I just want to make sure there's some scales larger than the box size, right?
Now, if you look at operational data, you see a flashy spectrum until you get to about wave number sort of 6 or 7, and then it starts nosediving at a minus 5/3 rate.
Right. Yeah.
It's that flashy bit at the top.
Well, my geometry is, triply periodic cube. I mean,
Well, your
but it's
pictures
going to depend on
look
that.
very like operational analyses, actually. That's why I asked the question.
Yeah. Okay.
There's a question over here.
That's just fortuitous.
That's luck. Okay.
Yeah.
There's a question over here.
Do you think of the unbalanced motion as being excited at large scales and cascading down, or is it excited?
Well, I wrote a paper with you on that, didn't I? Yeah, and Keith. The transfer is the transfer is at the large scales, and most of those pictures, the peak in the even the unbalanced part, the last one I looked at, maybe if time permits. The peak is actually, in the largest scales. I mean, I would presume in turbulence you have these infrared spectra, which are usually violet, right? So I presume that's being excited by something near the deformation scale. Yeah. But I don't have much proof. Yeah, sorry.
Oh, fine. Maybe that's a good time to end. So thank you very much.
Thank you.